Okay, so for chapter 20, the carboxylic acid derivatives, we're gonna go over nucleophilic acyl substitution or NAS, and there's two key steps for this. The first step is addition of a nucleophile to the carbonyl, and the second step is gonna be elimination of the leaving group. So you could basically think of this as substituting the leaving group with the nucleophile overall, and there's a tetrahedral intermediate in the mechanism. And there are going to be different leaving groups which can affect the rate of the reaction, right? So the first step here, addition, is going to prefer a stronger electrophile, which is a larger partial positive charge on the carbonyl-carbon right here, right? And the leaving group affects that positive charge. So we see here that this carbonyl could do resonance by pushing one of the bonds of the double bond into the oxygen, creating this intermediate here. And then this leaving group right here can do resonance if it has a pair of electrons to make a double bond right there, giving us this resonance structure over here. And this right here is the minor resonance structure because this carbon here does not have the full octet. And that's the number one reason for the major resonance contributor, right? So if chlorine is the leaving group, the chlorine is an overall electron withdrawn group, and it has poor resonance because it's a big atom. It has poor p orbital overlap, right? So the chlorine here cannot really do resonance with that carbonyl right there. So this carbonyl carbon is not going to gain as much electrons from this chlorine. So it has an overall large positive charge at the carbon because chlorine does not donate electrons to it. If you look at oxygen, oxygen is less electronegative than chlorine. So oxygen is going to donate electrons to the carbonyl, giving that carbonyl more electrons and making it less positively charged, more negatively charged, right? So the carbonyl carbon here has a smaller positive charge than the carbonyl carbon of the acyl halide because the carbonyl carbon of the ester is gaining more electrons from this oxygen right there. Now, nitrogen is the least electronegative compared to oxygen and halogen. So nitrogen is the most willing to give up its electrons and donate and do resonance. So that's why the carbonyl carbon of the amide is going to be the smallest. Right, so the least electrophilic, weak electrophile. Lots of electron donation by nitrogen, lots of carbon double bond nitrogen bond right here. Poor electrophile. Okay, so this is going to be the reactivity ranking list of the carboxylic acid derivatives. Acyl chloride is the most reactive derivative, and then amide is the least reactive derivative. Amide is the second most, ester is the third most. Now, the second step, elimination, we're going to prefer a better leaving group, where the leaving group is going to be able to leave with that pair of electrons where the bond gets kicked off. So we see that this chlorine here is a good leaving group because when we kick off the good leaving group, this chlorine with the negative charge can be stable because chlorine is very electronegative, right? This anhydride right here, leaving group, if it leaves with a negative charge, it's also stable because this negative charge on the oxygen here can do resonance with that carbonyl right there. This OR right here is not a good leaving group compared to the other two that we just talked about because it has a negative charge on the oxygen that cannot do resonance, right? But this one here is the worst leaving group compared to all of these because nitrogen is the least electronegative atom and it cannot do resonance, right? So these leaving groups here, you could think of them as the conjugate bases of the acids here. So the conjugate, so the acid of this conjugate base is HCl, the acid of the carboxylate is carboxylic acid, the acid of this alkoxide ion is this alcohol, the acid of this nitrogen with the negative charge is this amine right here. And if you look at the pKa of the acids, the lower the pKa, the more acidic it is, right? So HCl has the lowest pKa of -6 here, right? That means it's the most acidic, and it's the most acidic because when it gets rid of that proton and this chlorine gets a negative charge, this chlorine with the negative charge here is stable enough to exist by itself. So that chlorine right there is the conjugate base of this strong acid right here. Okay. Okay. Now, if we move on to the next one, we can follow relative activity of derivatives by hydrolysis. So this is an acyl halide, this is an anhydride, this is an ester, amide. hydrolysis is converting all of those derivatives into a carboxylic acid, the parent functional group, right? Acyl chloride is the most reactive derivative, so we don't need acid, we don't need base, we don't need high temperature. We just need water at 20 degrees Celsius to get that carboxylic acid right there with HCl. Now, the same for anhydride. We could do that as well. Like, think of this as the Lg, substitute the Lg with the OH to get the carboxylic acid, right? The Lg for the anhydride is this right here, which is going to leave in that form. And then we're going to just put an OH right there to get that carboxylic acid from the hydrolysis. Now, with the ester, if we're just given water with no acid, no heat, and like no base as well, there's going to be no reaction because the ester requires acid or base catalyst or heat to go through. Now, for the next one right here, we have an ester with an acid or base catalyst. So we can do hydrolysis with that carboxylic acid to get that carboxylic acid right there, right? But it takes hours to finish reaction because this is one of the lesser reactive derivatives. Now, amide is even less reactive, so it's going to require stronger concentration of acid or base to do hydrolysis here. Okay, it's easier to convert a more active derivative to a less reactive derivative, but hard to go the other way. Convert less active to more active. Okay, so acyl halide is going to be the most reactive derivative, form a lot of things. They're able to form this anhydride here using this carboxylic acid. And the mechanism here is going to be really tricky, right? But the way that I think about it is that this carbonyl here of the acyl halide is going to grab the proton from the other carboxylic acid. That bond right there is going to make a double bond right here. And then this double bond here is going to give this oxygen negative charge, which is going to attack that carbon right there. So if we can highlight where things are, this yellow oxygen there is this yellow oxygen here. This blue carbon here is going to be this blue carbon there. This pink oxygen here is going to be this pink oxygen here. And then this red hydrogen here is going to be... where is it? Let's see here. It's going to be this red hydrogen right there. So let me color code it again. And then let's say this purple carbon here is this purple carbon. Yellow oxygen is this yellow oxygen. Blue carbon is that blue carbon. The pink oxygen is that pink oxygen right there. And then this pink oxygen here is going to grab this red hydrogen, which is that right there. And then this oxygen here, which I'm going to color code in green, is going to be this green oxygen right here, which it reforms the carbonyl. Take out the chlorine. And then everything else is in place still, right? So the next one here is going to be hydrolysis of acyl chloride with water alone to get the carboxylic acid with HCl. We don't need acid, we don't need base, we don't need heat because it's the most reactive derivative. It could just happen in neutral conditions. Water could just attack the carbonyl carbon of the acyl halide, push the bonds with oxygen right away to get to this product here, carboxylic acid parent functional group there. If we react with an alcohol, we're going to create an ester, right? The easy way to predict the product here is to kick out this good leaving group chlorine and substitute that with the nucleophile right here, right? -1 hydrogen. So that's going to be this right here, right? Wait. Yeah, so this one here should, this is actual carbon right here. It should be like that. And then this should not be there. This should not be there, right? This right here is this nucleophile right there, right? And this Cl gets kicked off in the form of HCl, like that, okay? And T or pyridine neutralizes the HCl as it forms because this is an acid right here. And then you could just put a base like triethylamine or pyridine to deprocyanate that acid in lab, right? Tertiary amines are poor nucleophiles. They don't react with acyl halides. Okay. So the next one here is going to form an amide from the acyl halide using 2 equivalents of the amine or 1 equivalent of the amine with thiopyridine. And the easy way to predict the product here is to substitute the leaving group with whatever the nucleophile is, which is this right here. 1 to be the nucleophile, 1 to neutralize the HCl. Yeah, so the first equivalent of the amine is going to act as a nucleophile, which is going to attack the carbonyl. And then the second equivalent of the amine is going to neutralize the HCl. So let me draw that mechanism out for you guys to show what that means. Okay, so let's use that same reactant. Let's say we have this acyl halide right here. And we react it with 2 equivalents of this amine right here. Now, here's a quick way to predict the product quickly without doing the whole mechanism. We see that this is a leaving group right here. We're going to substitute that leaving group with this nucleophile minus 1 hydrogen. So we're going to copy and paste everything else. That's the decoration. That's going to be the same right there. This bond right here between the carbonyl-carbon and leaving group is now going to be attached to this nitrogen, which is the nucleophile, which is attached to a 1, 2, 3 propyl group. So 1, 2, 3 propyl group like that, 1, 2, 3. And then this nitrogen here is attached to hydrogen. And we're going to take away 1 hydrogen to make it neutral, right? Because if it had 2 hydrogens still, this nitrogen would be positively charged. Now, here's the mechanism, and here's why we need 2 equivalents of the amine to do this amide formation mechanism from an acyl chloride. So this acyl chloride here is very reactive. This carbonyl-carbon has a big partial positive charge because this bromine here is electronegative, so it's going to pull on the electrons of that carbon, making it positively charged. And because bromine is a big atom, it cannot do resonance very well with the carbonyl, so it can't donate electrons to the carbonyl as much. So this carbonyl-carbon here is not gaining electrons, right? And because it's not gaining electrons, it's not gaining negative charge, it's going to become a big positive charge. Now, this neutral amine here is able to attack that carbonyl-carbon right away, push the bond onto the oxygen, and then give us this tetrahedral intermediate right here, right? Where the carbonyl becomes a single bond O minus. This is the neo bond between this carbon and this nitrogen right here. And then this nitrogen here is attached to a 1, 2, 3 propyl group, which is this 1, 2, 3 propyl group right there. And then this nitrogen here is still attached to 2 hydrogens. So those 2 hydrogens are going to be like that with a positive charge. And then we're going to now reform the carbonyl, kick out the bromine, and get this intermediate here. 1, 2, 3. Hydrogen, hydrogen, positive charge. And then this Br minus right here is going to deprotonate that to get this final product here. But HBr or HCl is going to be in the form of gas, which is toxic, but we can neutralize this right away with the second equivalent of the amine that we have in the reactant, right? So this is for like Lievens class, like she uses the X minus, like it could be Br minus or Cl minus to deprotonate this. But in other classes, you might see the second equivalent of the amine deprotonating the positive charged nitrogen itself, right? But for Lievens, she will use the X minus to deprotonate it, forming the HX, right? Which will then get deprotonated by the second equivalent of the amine to give you this ammonia ion and this X minus ion, Br minus ion, right? So the first equivalent of the amine is used here as the nucleophile to attack the carbonyl-carbon. The second equivalent of the amine is used as a base to deprotonate the HX in the mechanism right there. Okay, So the next one here is going to be this acyl halide reacting with an amine, one equivalent, or one equivalent T, to form this amide, right? Because it doesn't have to be two equivalents of this amine. You could use one equivalent of the amine and then one equivalent of a base like T or pyridine, right? Or pyridine as the base, right? Pyridine as the base to deprotonate the HX. Okay. And then this one here is talking about like some tricky examples. There's two nucleophiles here in this molecule, the alcohol and the amine, but the amine is a better nucleophile because the nitrogen is less electronegative than the oxygen. And because the nitrogen is less electronegative than oxygen, it's more willing to give up its electrons and attack the electrophile. Oxygen is more electronegative than the nitrogen, so it wants to keep its electrons. It doesn't really want to attack the electrophile, right? So this nitrogen here, because it's the better nucleophile, is going to attack the carbonyl right there, push the bond onto the oxygen, and give us this tetrahedral intermediate here. And then from here, once we get that tetrahedral intermediate, we're going to reform the carbonyl, kick out the good leaving group chlorine to get this here. But this nitrogen here cannot be deprotonated or neutralized because it has a full positive charge and it has no protons. It has no hydrogens that's attached to. So this is unstable, right? So the next thing that's going to happen is that this oxygen here with one of its pairs of electrons is going to attack this carbonyl-carbon, push the double bonds to the oxygen, and then the O- is going to go back down and kick that out as a leaving group, right? So this bond here, which I'm going to highlight in pink, the two electrons of that bond are those two electrons right there, that pair of electrons of nitrogen right there. When we kicked out this LG, neutralizing it, right? But it looks like to get to this product here, you could just attack this electrophile using the alcohol directly and then get here directly. But then that's not the whole mechanism. The mechanism is using this first as the nucleophile because it's a better nucleophile, getting to this intermediate first, and then we get to this point afterwards. Okay. Okay, so the next one is going to be talking about carboxylic derivatives reacting with strongly basic nucleophiles like organometallic reagents or hydride reagents like reducing agents. So this first one here, we have an acyl halide reacting with two equivalents of organolithium, RLI. It's like a green reagent. The carbon that is directly attached to the lithium is negatively charged. That's the nucleophile. That's going to attack this electrophile here, push the double bond to the oxygen, get this tetrahedral intermediate. We're going to reform the carbonyl, kick out the chlorine, get this ketone here, but we do not stop here because this carbonyl-carbon of the ketone is still electrophilic for this RLI to attack, push the double bond to the oxygen to get this alkoxide intermediate, right, where we have RO minus, and then we do acid workup in the second step to protonate the O minus to get this alcohol here, right? And notice how we added the R group 2 times to the acyl halide, right? The R group is this ethyl group here, which we added that 2 times to that molecule there. Okay. Now, if you want to use a less reactive organometallic reagent and only add the R group once, you can use an organocuprate, which stops at the single addition to form a ketone, right? And the organocuprate is going to be in this form right here, where we have R2CuLi, but you're only going to add the R group 1 time to the derivative. So this is our R right here, which we're going to substitute that R with that bromine, which is this product right there, right? And these are just the side products there. Now we could use hydride reagents or like reducing agents like NaBH4, the weak reducing agent, or LiLH4, the strong reducing agent, to reduce these down, right? So this acyl halide here, the most reactive derivative, can work with the weak reducing agent, sodium borohydride, to eventually get the primary alcohol, right? So you're going to get rid of the leaving group and then convert the carbonyl to the alcohol right here. The intermediate is going to be an aldehyde, but it's going to be reduced into a primary alcohol because NaBH4, there's 4 hydride ions, 4 H minuses that can reduce that down to that prime alcohol there. Now, if you want to stop an aldehyde from this acyl halide, you got to use a bulky, less reactive hydride donor, which is this bulky lithium aluminum triterbietoxide reducing agent here, which will stop at the aldehyde there. Okay. And it's less reactive because there's a lot of oxygens here doing electron withdrawing to this hydrogen, making it less negatively charged, less reactive. Now, anhydrides are less reactive than acyl halides, but they react the same way. You could do hydrolysis with neutral water. You could do ester formation with neutral alcohol. You could do amide formation with neutral amine, right? Now, here's a challenge. There's 2 carbonyls, right? Which one is gonna act as the electrophile? Which one's gonna be the leaving group, right? Which one is gonna get attacked by the nucleophile? For the symmetrical anhydride, it doesn't matter, right? Because you're gonna get the same answer either way. Like let's say this right here in red is the electrophile. That means that this right here is the leaving group, and the leaving group is gonna leave in the form of carboxylic acid, and then the electrophile is gonna have this neonucleophile attached to it like that. But if you did the other way, this would be the leaving group, which will become that, and then this would be the nucleophile, which will become that. And because it's symmetrical, there's no issue there. But if it's asymmetrical, you get a mix of products, right? Like this could be the LG, resulting in these products here, right? Or this could be the LG leaving group, resulting in these products here, right? So those are the mix of products if you had an asymmetrical anhydride. The second big problem is that you're gonna waste half of the molecule. It comes off with this leaving group, trash, so use anhydrides when simple and cyclic. So half of the molecule is get lost as carboxylic acid, and that could be messy in lab, right? This is an alcohol here reacting with an anhydride, forming an ester right here, right? So this alcohol is the nucleophile, which is gonna attack the carbonyl-carbon of one of the carbonyl-carbons of this symmetrical anhydride, and then this is gonna be the leaving group, right, which is going to be left in the form of carboxylic acid, and we substituted that leaving group with this nucleophile here, which is that nucleophile right there. Okay. This is a cyclic anhydride with alcohol. So because it's symmetrical, it doesn't matter which carbonyl is the electrophile. Let's say it's this one right here. That means that this is going to be our LG. So this is going to become a carboxylic acid, and then this carbonyl-carbon is going to have an ester, which is attached to this OR right there, which is this right here, right? And this carboxylic acid here came from this right here, like that. Okay. Big bonus to anhydrides, less difficult to handle than acyl halide, less air, water reactive, don't form HCl. Esters, they're less reactive as electrophiles. So they're slower at nucleophilic acyl substitution. They're an okay leaving group because they're going to leave with an OR minus. The negative charge is on the oxygen, which is relatively electronegative, but it can't do resonance like the carboxylate, and it's not as electronegative as the chlorine or bromine. Right? It's easier to handle, common in nature, need catalyst like an acid or base catalyst with heat or harsher conditions to react. So you could do hydrolysis of ester to convert this ester to the carboxylic acid using acid, water, and heat. Where the mechanism is going to be the nucleophilic acyl substitution in acidic conditions, right? First step, protonate the carbonyl oxygen to make it activated. Second step, addition of the nucleophile, push the double bond oxygen, get this tetrahedral intermediate. Then we do the proton transfer where we protonate the group that we want to kick out, deprotonate the group that we want to keep at the same time. And then we eliminate the good leaving group by reforming the carbonyl, kick out that good leaving group, get this protonated carbonyl here, and then the last step is to deprotonate this positive charged carbonyl to get this neutral product there. Don't forget the side products throughout the mechanism. And this is in equilibrium as well. If you have a lot of water, it's going to go towards the carboxylic acid product because the water is that OH right there. If you have a lot of alcohol, it's going to go towards the ester, right? Because this is in equilibrium. You could protonate this carbonyl oxygen, and then if you have a lot of alcohol, this alcohol can attack that carbonyl and go all the way back to the ester right there, right? Okay. Now in base, there's a specific name for hydrolysis of esters in base, and that's saponification, where you get this carboxylate ion here, which is used in soap, right? Because this is the polar end of the soap, and then the R chain is the non-polar end of the soap. Now, here's the mechanism. We don't have to proton the carbonyl right away because this OH- is a strong nucleophile itself, directly attacking the carbonyl. Push the double bonded oxygen, get this tetrahedral intermediate. We reform the carbonyl, kick out that leaving group OR, and then because we're in basic conditions here, this OR- here is gonna deprotonate the carboxylic acid to get this carboxylate ion there. Okay. Now in trans esterification, that's converting one type of ester to a different type of ester, and this can happen in either acidic conditions or basic conditions. Right, so we're gonna need excess alcohol to force equilibrium. So this is the OR of the original ester. This is the new ester with the new OR group, and this new OR group comes from this reagent here, the methanol. And this is in acidic conditions because we have H2SO4, right? And then the leaving group just leaves as a neutral product because when it leaves, it's gonna leave with a proton, right? When you do the whole mechanism of nucleophilic acyl substitution in acidic conditions, it's very similar to hydrolysis, right? But instead of water as the nucleophile, you have alcohol as the nucleophile. Now in basic conditions, you get the same product, right? You substitute the OR with the new OR, but this time, if you're still in basic conditions with no acid workup, you end with an alkoxide ion, this O- right there, right? Here's the mechanism. Attack the carbonyl right away, push the double bond oxygen, reform the carbonyl, kick out the OR leaving group to get this ester here with that OR- leaving group right there. And the same Le Chatelier's principle happens there. Right, we could do it in cyclic as well. Where let me just do this mechanism to show you guys how it works here. Okay, so we can have this. This, and then we have this ethanol in acidic conditions. So because we're in acidic conditions with a cyclic ester or lactone, the first step, protonate the carbonyl oxygen of the ester to make it activated. Now, once that's activated, the weak nucleophile alcohol here can attack the carbonyl carbon, push the bonded oxygen, and give us this tetrahedral intermediate here. Okay, now from here, we do the proton transfer step where we deprotonate the group that we want to keep, which is this new group here. We want to keep the new group, and we're going to protonate the old group, which is this group right here. So we're going to do it at the same time like that, and get this new tetrahedral intermediate here. Okay, now once we have that, we're going to reform the carbonyl here. This bond right here is going to break and kick off that leaving group to give us this final product here. Okay, now once I have that, I am done with the mechanism. All right, let me double check. Boom, boom, boom. Yeah, that's good. Okay, and that should be this as well. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yep. Okay. Okay. Nomenclature. Esters can form amides, but not as easy. We need a lot of heat. Because we're trying to form a less reactive derivative, and esters is not like a reactive derivative. So let's say we have this ester right here with heat and an amine. We can substitute the leaving group with this amine right here, but we need a lot of heat, right? And it's low because an ester is a poor electrophile, and we're using a neutral nucleophile, which is the neutral amine. Here's the mechanism. the neutral amine here is going to attack the carbonyl-carbon, push the double bond with oxygen, get this tetrahedral intermediate. Then we're going to protonate the O-, deprotonate the amine to get this right here, right? This is different because we're used to deprotonating the new group and protonating the old group at the same time, but we're not protonating this OR right here because this neutral oxygen here is not basic enough to grab the proton from this nitrogen, right? Because if you think about it, like the neutral nitrogen here is less electronegative than this neutral oxygen here. So yeah, this neutral oxygen here is more electronegative than this neutral nitrogen. So this nitrogen here is more basic, right? It's more willing to give its electrons to attack. So because it's more basic, it's going to keep its protons. But this oxygen with the negative charge is less stable, more reactive. So that's why this O- is going to deprotonate this amine to get this neutral tetrahedral intermediate, which then we reform the carbonyl to kick out that OR- leaving group to get this intermediate. And then the OR- leaving group deprotonates the carbonyl to get this neutral product here. Okay, this right here is not ideal in lab. The preferable way to do it in lab is through an acyl halide or anhydride, the top two most reactive carboxylic acid derivatives. Okay, esters can undergo nucleophilic acyl substitution, carboxylic acids, other esters, amides. We can also react it with strongly basic irreversible nucleophiles like organometallics. So let's say we have two equivalents of the organometallic here. We're going to add the R group 2 times, right? So this leaving group is going to leave, and we're going to add the R group 2 times. And because the R group is 1, 2, 3 carbons, 1, 2, 3 carbons, this is also going to be 1, 2, 3 carbons, right? Where we add the R group 2 times. And here's the mechanism. The carbon directly attached to the MGBR is a nucleophile, which is going to attack this carbon here, push the double bond oxygen, get this tetrahedral intermediate, and then we're going to reform the carbonyl, kick out the OR leaving group, getting this ketone. And this ketone here is an electrophile, which is second equivalent of the MGBR is going to attack that ketone, push the double bond oxygen, get this tetrahedral intermediate, 1, 2, 3, 1, 2, 3, which is the alkoxide ion. And then we're going to protonate the alkoxide ion to get this neutral alcohol here, right? So this is nucleophilic acyl substitution because we're substituting this OR with this R group. And then this is nucleophilic acyl addition because we're just adding on the R group without eliminating anything. And then this right here is acid workup where we protonate the O- to become the neutral OH right there. Okay. We could do that with a lactone or a cyclic ester as well. And here's the mechanism. We have a CH3I where the negative charge here is a CH3, which is going to attack this carbon, push the double bond oxygen, and then we're going to get this O- right here. This is the CH3. This is the O-. Oh, wait, no. The O is still attached there. And then let's now reform the carbonyl, kick out that oxygen to get this intermediate here, which is a ketone. The methyl group is there, which is nil. And then from here, the second equivalent of the CH3I, Li, is going to attack the ketone, push the bond with oxygen, and then get this intermediate right here, where we get O-, the two methyl groups that are neo, and then this O- right here, which will then get protonated by the H3O plus second step to become neutral alcohols like that. Okay. And then you could redraw it into this linear form, which is neater, but on the exam, if you draw it like this, you should get full credit as long as it's clear and like this and this is not connected, like as long as it's like clear that they're separate. But if you have time, you could try linearizing it or making it neater like that. Okay. Now we could also use reducing agents like hydride reagents. Like we could use lithium aluminum hydride to reduce this ester to this primary alcohol. And all you did here is get rid of the leaving group and convert the carbonyl to the primary alcohol like that. And here's the mechanism. This hydride ion, H- comes from the LiLH4, attacks the carbonyl carbon, push the bonds with oxygen, get this tetrahedral intermediate, reform the carbonyl, kick out the OR group, get this aldehyde, and then the second H from the LiLH4 attacks the carbonyl carbon of the aldehyde, push the bonds with oxygen to get the O-, and then you bring in the second step of H3O plus to do acid workup to convert the O- into OH. Okay. Now there's a specific reducing agent that can add once to the less reactive carboxylic acid derivative, which is diol, right? Diol is gonna convert 3 functional groups to the aldehyde. they're going to convert the ester, amide, or nitrile to an aldehyde, right? And we just need one equivalent of that, like that, okay? We see here this is an ester. When we use dibo with acid workup, we convert that ester into this aldehyde right there. Okay, and esters can also form enolate ions because the most acidic proton of this ester here is going to be this alpha hydrogen back in the 1 B. We use a strong base like LDA. We're going to deprotonate that alpha carbon to generate this enolate ion. And then because this enolate ion here can do resonance, the negative charge on this carbon here is less stable than the negative charge on this oxygen. So the nucleophile is this alpha carbon right here, right? And then we can use that nucleophile on the alpha carbon to do SN2 reactions, right? Because let's say here the LDA grabs the alpha proton, generates the enolate ion, and then once we have this enolate ion over here, we could reform the carbonyl, have the alpha carbon attack an electrophile, kick out a good leaving group to do SN2, where this could be the star carbon, this could be the dot carbon, and then this right here could be the new bond between the star and dot carbon, like that. Okay? Okay. So these are some information that you need to know about esters. They could be waxes, they could be fruity scents, they could be fats and oils, they could serve as lipid bilayer, right? These are just conceptual stuff or vocab that you need to know. The last, or like one of the last carboxylic acid derivatives is the amide, right? And then nitriles afterwards. And then chapter 21 is about amines, right? Okay. Amides, least reactive electrophile out of all of the carboxylic acid derivatives, because nitrogen is the least electronegative, doing the most amount of resonance, reducing the positive charge of this carbon, making it the least electrophilic. There's limited rotation around this bond right here, the carbonyl nitrogen bond, because of the resonance it could do, right? Because the nitrogen here is donating electrons, this resonance structure here is around 40%, and because there's a double bond right there, that double bond cannot do free rotation. So it's limited rotation around that bond. All right, and then you can see that on the NMR. Proteins are linked by amides, hard to break apart, relatively rigid fixed structure, not impossible to do NAS, hard uphill process, loss of heat, loss of catalyst. We could do hydrolysis. We can convert the amide to the carboxylic acid using acid, water, and heat. Same mechanism as before. We could do it in basic conditions to end it with the carboxylate ion. The mechanism is here. Attack the carbonyl, push the bond to the oxygen, get this tetrahedral intermediate, reform the carbonyl, kick out that leaving group to get this carboxylic acid. But because we're in basic conditions and we kick out this bad leaving group here, this bad leaving group that is unstable is gonna deprotonate the carboxylic acid to this carboxylate right here, right? And then we could also use a reducing agent with lithium aluminum hydride to then reduce the amide down by getting rid of the carbonyl directly to give us this final amine right here. So we could use an amide to an amine just by getting rid of that carbonyl right there. And here's the mechanism. The hydride ion or reducing agent can attack the carbonyl carbon, push the double bonds to oxygen, get this tetrahedral intermediate, and then this O- here is going to attack this aluminum ion, which has 3 bonds in an empty p orbital to create that right there, which is going to be the leaving group. And then this nitrogen here is going to form iminium ion, which is a carbon double bond nitrogen with the positive charge, and kick out that leaving group. And then this H- here, a second equivalent of it, is going to attack that iminium ion carbon, push the double bonds to oxygen to get this amine right here. Okay, so we're gonna use neutral water in the second step, because the third step, H3O plus, if there's acid, right? We said earlier that amines are relatively basic because of the less electronegativity attached to the nitrogen. If we're in acidic conditions, that amine is gonna get protonated to become an ammonium ion with a positive charge and a hydrogen, like that, right? Now we could use dibo, like we said earlier. Dibo reduces esters, amide, or nitriles to the aldehyde like that. We could do Hoffman rearrangement with a primary amide with NaOH, Br2 or CO2, water, and heat to convert that primary amide to this amine right here. And the most important thing about this reaction is that we get rid of the carbonyl carbon. We lose one carbon here. So this is important for synthesis, right? So the carbons coming off of the ring are 1, 2, 3. But when we see over here, when we do Hoffman rearrangement, we completely convert this primary amide to this amine right here, where we lost that carbonyl carbon right there. And now there's only 2 carbons coming out of the ring like that. Okay, that carbon right there, carbonyl carbon, came out in the form of CO2. And here's the mechanism, which I recommend writing down in your note card because it's a little bit tricky with the migration steps. Right. Now nitriles, we could do hydrolysis, right? Where the carbon of the nitrile here is going to be the carbon of the carboxylic acid in acidic conditions or basic conditions. The mechanism is pretty long, right? You're going to first get to the amide, and then once you get to the amide, you do hydrolysis again to hydrolyze the amide into the carboxylic acid. Same here in basic conditions. We could also do organometallic reagents with nitriles, but here's the important thing for nitriles. When you do organometallic like Grignard reagent or organolithium, you won't add the R group 2 times. You're going to add the R group only 1 time, which is that right there. Where this carbon here of the nitrile is going to be that carbon there of the ketone. And this is the R group that we added only 1 time, like that. Okay. And here's the mechanism. This R minus is going to attack that carbon, push one of the bonds of the triple bond onto the nitrogen to get this carbon double bond nitrogen with a negative charge. And then we do acid workup to over-protonate the nitrogen to get this iminium ion. And then this iminium ion can do hydrolysis into the ketone back in 118B. Right, I don't think that would be tested, but like just in case, that's a 118B reaction right there. Okay, and like I said earlier, dibol reduces an esters, amides, and nitriles into aldehydes. This is a nitrile. We use dibol. This nitrile carbon becomes this aldehyde carbon right there. Now, when we use lithium aluminum hydride, we reduce the nitrile into the amine right there. And be careful, this carbon of the nitrile here is still there like that, right? So we see 1, 2, 3 carbons coming out of the ring. That's 1, 2, 3 carbons coming out of the ring like that. And for synthesis, you can see something like this, where we have this haloalkane right here. And then you see 1 step NaCN, like first step NaCN, second step lithium aluminum hydride, and then second step water, third step water. And the answer here is going to be this, where we have an extra carbon coming out of the ring. So before we only have 1 carbon coming out of the ring, but now we're going to have 2 carbons coming out of the ring with an amine, primary amine, NH2, right? Because the first step here is to substitute the Br with the CN through an SN2 reaction, right? The CN minus attacks that carbon, kicks out the Br to get this nitrile. And then from here, after the second and third step of the reducing agents, this nitrile right here carbon is that carbon right there. So do not forget about that. And that's the extra carbon that came from the first step, the cyanide ion. Okay. Carbonyls are polar, nitriles are polar. We could reduce that with hydrides like NaBH4 or LiLH4. Alkenes or alkynes are nonpolar because they're bonds between the same atom, carbon and carbon. So we reduce with hydrogenation, H2PDC. Nitriles are less polar than carbonyl. So we could use hydrogenation like H2PDC to reduce nitriles down into NH2. So like this right here, instead of using LiLH4, we could use hydrogenation reagents, H2PDC, to reduce the CN to this NH2 right there, right? Where the C of the CN right here is going to be that C right there of the primary amine, like that. Okay. Now, we could move on to chapter 21, which is going to talk about amines. We have a primary amine where this nitrogen here is only attached to 1 carbon. We have a secondary amine where the nitrogen here is attached to 2 carbons. We have a tertiary amine where this nitrogen here is attached to 3 carbons, right? And then nomenclature, practice with that. Let's see. Yep. So properties, spectroscopy. Amines can act as both an acid or a base. If it acts as an acid, a base is gonna come around to deprotonate it to give us this alkyl amide ion, where we get a negative charge on the nitrogen. If it acts as a base, it's gonna grab a proton to become this ammonium ion, alkyl ammonium ion, right? A common amide ion is LDA, right? Which is this right here, or T, triethylamine. Okay. Ammonium ions can act differently depending on if they're primary, secondary, or tertiary. Oh yeah, this is pretty tricky right here. Let's see. This is this is let's see here. Alkyl donates electrons, so there's gonna be more negative charge on the nitrogen, harder for it to lose protons, better base, weaker conjugate acid. Yeah, so this right here has the lowest pKa, it's the most acidic because there's no R groups in the way, and there's a lot of positive charge around on the nitrogen, right, making it very acidic. The pKa over here is higher because there's R groups in the way, donating electrons to the positive charged nitrogen, making it more stable, and then making it less reactive, less acidic. But the reason why this one is less than this one is because of the solvation show, right? So this one here is very important for vocab especially. Know the differences between the pKa's of the ammonium with no R groups, the ammonium with 1 R group, the ammonium with 2 R groups, and the ammonium with 3 R groups, right? Because it rises as you increase the R groups until you get the tertiary ammonium ion, which is going to be in between the ammonium with no R group and the ammonium with 1 R group, like that, okay? Loss of steric hindrance, poor solution of charge, uncountable in solution, okay. Okay. Have resonance. Yeah, so this pair of electrons here is not going to be basic or reactive because it can do resonance with the benzene ring right here, making it stable and less reactive. Okay. Hybridization, sp3, sp2, sp. More S character, more acidic because closer to the nucleus, which is going to stabilize the negative charge. Formation of amines. The first one is over-alkylation, where this amine here can do SN2 with an Ri. And it gets deprotonated to become neutral. And when it becomes neutral, it can attack another electrophile to get this right here. And then we could like get the positive charge and keep going until we get this positive charge on the nitrogen that can no longer be deprotonated, no longer be neutralized, right? Mixes of single, multiple, fully alkylated N, lots of excess alkyl. Yep. Positive charge on this nitrogen with 4 bonds. Okay. Lots of excess ammonia. Okay. Now, the better ways to do it is going to be reduction of nitrile, where once you get the nitrile here, you could reduce it with H2PDC or LiOH4 or nickel H2PDC, like we went over last time. Where this carbon of the nitrile here is that carbon right there. Reduction of azide, where this doesn't add an extra carbon, right? It just substitutes the bromine with the N3, and then the N3 becomes the NH2. No extra carbon to worry about there. Hofmann rearrangement, which we talked about in the chapter 20, converts this primary amide to this amine right here, where we lose that 1 carbon, right? Because before we had 1, 2, 3, 4 carbons, now we only have 1, 2, 3 carbons. Reductive amination is the new one. That's important. You're gonna have like a formaldehyde, aldehyde, or ketone reacting with an amine in slightly acidic conditions like pH of around 4 to create this iminium ion. And then once you get this iminium ion, you could use a reducing agent like H2PDC or NaBH2CN, which is the common reagent for reductive amination, with NiHCl3 to get this amine right here. And then you could do reduction of amide to completely get rid of the carbonyl to get this amine right here. You could react an amine with an acyl halide to create an amide, and then from that amide you could reduce it to get this new amine here. So that's another way you could add an R group to this amine here, right? And then from here you could do reductive amination to add another R group, right? Where this is going to be the new R group right there on the nitrogen, like that. Okay. There's a quick way to do reductive amination predicted product as well. Just substitute the carbonyl, the bond between the carbonyl carbon and oxygen with the new bond to the nitrogen right there, right? Like if I was to highlight this part right here in purple, that's that part in purple right there. The hydrogen is not invisible, but the carbonyl oxygen is now the amine that it reacted with in reductive elimination. And that's a quick way to predict the product when you do practice. Now, Gabriel synthesis, you're going to have this phthalimide, which is the common thing for Gabriel synthesis with a strong base, with a carbonate ion, which is going to deprocynate that nitrogen, give that nitrogen negative charge. This nitrogen negative charge is going to do SN2 by attacking that R, kicking out the X group to get that structure. And then from here, you could do hydrolysis with basic conditions to get this carboxylate ion and this neutral amine, or you could do hydrolysis in acidic conditions where you get this phthalic acid in neutral conditions. But the amine here is going to be overprotonated to become the ammonium ion because we're in acidic conditions here. Or you could use this amine to cleave the imide, right? And this can be a bond right here. And I think that there should be hydrogen here, there should be hydrogen here to be neutral, but you're gonna get the neutral amine, right? And that neutral amine is gonna come from this part of the phthalimide right there, which is that part right there. And this one here is overprotonated because we're in acidic conditions like that. Okay. So yeah, that's gonna be it for this session. Do you guys have any questions for that for this week? I know that was really quick, but I just wanted to go over the reactions and mechanisms today. Okay. Okay. If not, I hope you guys good luck on the midterm next week. And yes, I'll see you guys next time.